Ever seen a spider robot in action? Well, in this series we are crafting our very own. Using materials that are easy to find, we are crafting a DIY spider robot. And I'm inviting you to join me on this adventure. Now, a small confession. I'm learning as I go. Some challenges still puzzle me. And the beauty of this series is that we'll tackle them together, step by step. If you are new here, I suggest starting from the beginning to get a full experience. Throughout this series, I'll break down each part of the project, ensuring you can follow along with ease and maybe even kickstart your own robotic creation. I aim to keep these sessions short and to the point. However, if anything feels a bit rushed or unclear, don't worry, I've provided supplementary documentation and Jupyter notebooks to help reinforce and expand on what I cover. Remember, it's about the journey and understanding, not the pace. For those interested in the tools, you'll find all the details in the description below. Join me and let's embark on this exciting DIY voyage together. Welcome tech enthusiasts and future roboticists. You're tuning into our comprehensive tutorial series on building a spider robot. Whether you're just starting out or leveling up your skills, this guide is here to make your journey an enlightening one. Before we start, don't forget to check out my other tutorials in this series for a rounded understanding of the project. Each tutorial is crafted to build your skills, step by step. Find the complete series in the description below. Today, we're focusing on a crucial aspect of robotic movement in our spider robot, the forward kinematics method. Let's break down this concept and see how it brings our robot to life. Imagine each leg of our robot as a mini chain of joints and segments. Forward kinematics is our tool to figure out where the tip of each leg will be, based on the angles of these joints. Think of it like predicting where your hand ends up when you move your arm without looking. To understand this better, we need to touch upon some trigonometry basics. Trigonometry is all about angles and sides of triangles. Don't worry, we'll keep it simple. First, the sine of an angle in a right-angled triangle is a ratio. The length of the side opposite the angle to the triangle's longest side, called the hypotenuse. Cosine is similar, but it's the side next to the angle over the hypotenuse. Tangent is the sine divided by the cosine. Next, the law of cosines, a more generalized version of the Pythagorean theorem that applies to any triangle, not just right-angled ones. The law of cosines helps us relate the lengths of the sides of a triangle to the cosine of one of its angles. It's particularly useful in robotics, where we often deal with non-right triangles formed by the robot's joints and limbs. Now let's apply these concepts to our spider robot's legs using the forward kinematics naive method. We start by converting the angles of our robot's joints from degrees to radians. We use radians in these calculations because they provide a more natural way to describe angles in terms of their relation to the circle, which is essential in robotic movements. Next, we calculate the positions of each joint. Using sine and cosine, we find the x and y coordinates for our robot's coxa joint, coxofemur joint, and the femur tibia joint. First, we determine the x and y coordinates of the coxofemur joint. This joint acts like the connection point in a human leg, linking the body to the upper leg segment. Using trigonometry, we calculate xa, the horizontal position, ya, the vertical position of this joint. We multiply the length of the coxa segment by the cosine and sine of the coxa joint angle, respectively. This gives us precise coordinates based on our joint's current angle. Next, we focus on the femur segment of our robot. We calculate its vertical and horizontal components. The vertical component, G2, is found by multiplying the femur's length by the sine of the coxofemur joint angle, representing the vertical positioning of the femur tibia joint. Similarly, the horizontal component, P1, is the femur's length times the cosine of the coxofemur joint angle. This tells us the horizontal positioning of the femur tibia joint relative to the coxofemur joint. Finally, we calculate the x and y coordinates of the femur tibia joint. By applying the horizontal component P1 to our previous calculations, we can pinpoint this joint's exact location in space. The horizontal extension, xc, is determined by multiplying the length of the femur segment, represented by the horizontal component P1, by the cosine of the coxa joint angle. This gives us the horizontal distance from the coxa femur joint to the femur tibia joint. Similarly, the vertical extension, yc, is found by multiplying the same femur length, the horizontal component P1, by the sine of the coxa joint angle. This calculation gives us the vertical distance from the coxa femur joint to the femur tibia joint. Let's focus on the femur tibia joint, a key point in our leg's movement. The law of cosines helps us find one side of a triangle when we know the other two sides and the angle between them. In our case, the sides are the lengths of the femur and tibia segments, and the angle is at the femur tibia joint. Mathematically, it looks like this. By inputting the lengths of the femur and tibia and the angle at the femur tibia joint, we can solve for h, the straight line distance from the femur tibia joint to the tibia tip. With h known, our next task is to break this distance into horizontal and vertical components. This will give us the xb and yb coordinates of the femur tibia joint. For this, we calculate additional angles at the coxa femur and femur tibia joints. Using more trigonometry, we calculate these angles. We first find phi 1, the angle at the coxa femur joint, using the law of cosines again. This law helps us understand the relationship between h, the femur, and the tibia. This tells us the angle at the coxa femur joint. Phi 3, an auxiliary angle, is then determined by subtracting the original angle at the coxa femur joint from phi 1. These angles are crucial for determining the position of the femur tibia joint. Now we use phi 3 to find the horizontal projection PP of the femur tibia joint on the plane of the femur. This is calculated using the cosine of phi 3 multiplied by h. The horizontal distance between the coxa femur joint and the femur tibia joint. P2 is then the difference between PP and the horizontal projection of the femur. Finally, we calculate xb and yb, the x and y coordinates of the femur tibia joint. These are found by using the sine and cosine of the original coxa joint angle, multiplied by pp. The vertical component of the femur tibia joint, g1, is found using the sine of phi 3 and h, and it might be negated depending on the robot's coordinate system orientation. Now, let's connect the dots between our calculations and the robot's joint positions. Each of these intricate calculations, from the law of cosines to the determination of angles phi 1, phi 3, plays a pivotal role in pinpointing the exact location of each joint in the robot's leg. The x and y coordinates we calculated for the coxa femur and femur tibia joints, xa, ya, xb, yb, and so on, are more than just numbers. They represent the precise spatial coordinates where each joint should be positioned. By mapping these coordinates onto our robot, we can visualize and control the movement and articulation of each leg with incredible accuracy. This precise mapping is what allows our spider robot to move fluidly and respond accurately to our commands, making the journey from mathematical concepts to mechanical reality. With our calculations complete, it's time to bring our spider robot's leg to life in the virtual world. Let's see how we map out its joints in our code. Here, we're creating a list that represents the locations of each joint in the leg. This list is the bridge between our mathematical calculations and the robot's physical structure. We start with the origin point, 0, 0, 0, the base from where our leg begins. Next, we add the coordinates of the coxa femur joint, calculated earlier as xa and ya. This joint is crucial as it connects the leg to the robot's body. Then, we move to the femur tibia joint, crucial for leg articulation. By adding xc and yc to our initial coxa femur coordinates, and including the vertical component g2, we locate this joint precisely in three-dimensional space. Lastly, the endpoint of the leg, which interacts with the ground. Its coordinates are determined by adding xb and yb to the coxa femur coordinates, and using g1 as its vertical position. This marks the endpoint of our leg's journey, and there you have it. By applying these trigonometric principles, we've precisely determined the position of the femur tibia joint. I hope this tutorial lit up your path in the fascinating world of robotics. Stay tuned for more, and happy coding.